concepts and formulas, you learn more last year.
I don't know.
No chance, man.
Yeah, maybe. The amount of work you do, you must spend 10 times more work or time on your work. Yeah.
Let's take a field trip. Let's just like switch classes to get one HFM, so they really get.
Not a bad idea. Okay, so we jumped to chapter 17. Thermodynamics. People are asking, well, what's the difference between thermochemistry and thermodynamics? Thermochemistry is strictly about the heat flow in or out of a chemical reaction, where thermodynamics is going to involve not only the heat flow, which is included in thermodynamics, but also the particle motion and the particle arrangement is going to matter with thermodynamics. Yes?
Two things. First of all, do people find like this hard in thermochemistry? Is that what makes this whole unit hard in thermodynamics?
Hi, Mr. Buckheim. How are you? I'm good, thanks. Nice to see you. Haven't seen you all year.
Try to hide.
Yeah, I tried to. I don't know. I mean, Nav was complaining the other day. Is like, well, when is this going to get hard? It's really simple. I think you're going to find the same thing with thermodynamics. It's going to every day when I teach you something, you're going to be like, well, yeah, that seems pretty easy. But then, I don't know. When you start the practice test, I think you're going to see that when we start getting into the core concepts and using them and interpreting them, it's challenging.
My second question was, why is there jerky?
Just for the season. For the season. Yep. All right. Now, you're going to hear me talking about whether a reaction is spontaneous or non-spontaneous. Spontaneity is a big deal in chemistry. Whenever we have a reaction that's going to happen, it's just going to happen under the set of conditions that we're in, that would be a spontaneous process.
Go against like, the definition of spontaneous. The spontaneous is like it'll happen anytime. Maybe it's not
Mr. Moore, for our particle drawing, is it only for one particular thing?
Just one of the reactions. And the word spontaneous means it's like when you hear of a person being spontaneous. Oh, I like that person, he's so spontaneous. It just means that that person does things without any careful planning. They just want to go and do, and they want to be kind of carefree. In terms of a reaction that's spontaneous is one that you don't have to persuade to happen. You don't have to continually add heat. It's just going to happen. For instance, if you put a rusty or an iron hammer into hydrochloric acid, that will rust. You don't need to heat it up. You don't need to cause a high pressure. It just happens. The magnesium that you put into HCl yesterday or the day before, that was a spontaneous reaction. You just put these two together, and you don't have to do anything else. They just react. Now, if I were to take a sheet of paper, and I want to light this on fire. Now, we know that paper will burn. But sometimes spontaneous reactions, they'll take a little bit of a boost. And we call that boost the activation energy. So I do want to mention that because sometimes a lot of spontaneous reactions, they'll need a boost to get started, but once they get started, they just go on their own. And that would still be considered a spontaneous reaction, even if it needs a boost. Like this, if I want to burn this, I'll take a match and light the match, and then I'll hold the match up to the paper. What is that doing? That's just providing a little bit of energy for the reaction to get going. And once the reaction gets going, I can take the match and throw it away, and this will just burn on its own. That's a spontaneous reaction. If it weren't spontaneous, I would have to continually hold the match there, and as soon as I take the match away, the reaction would stop. That would be a non-spontaneous reaction. So spontaneous means that it will happen under the set of conditions, but it may need a boost. And so that boost, we'll talk about that boost in the next chapter. That's on reaction kinetics, which involves activation energy. Now, what causes a reaction to be spontaneous? How do we know if something is going to be? Well, back when chemistry was a baby and we didn't really understand what caused things, people first thought that when a reaction was exothermic, if it could get rid of some of its stored heat, that would make it spontaneous. We find out that that's not always true. I mean, we think of like the example of the ball on the hill. we just give that, then that's got lots of potential energy. And if we give the ball a kick, then it will convert the potential energy into kinetic energy, and the ball falls spontaneously. And it changes the kinetic energy spontaneously. People thought, well, if chemicals have energy stored inside of them and have a chance to get rid of some of that and go to a lower energy state, that will just happen spontaneously. But we find out that that's not true. Now I'm going to uncover a picture that's really sad, and I don't even like to look at it myself. So I hope that it doesn't change your mood or depress you.
What?
But this is an example. Isn't that sad? A dropped ice cream cone that's melting on the floor.
I'm crying.
Me too.
Yeah.
That thing looks really good. But anyway, this would be an example. This is an endothermic process. When a solid melts, it's endothermic. It has to take heat in. And that's what's happening in this picture. I can't even hardly look at it.
We're talking about the turkey.
No, the ice cream.
Is it because turkeys are...
Yeah, something like that. So yeah, this kind of example tells us, yeah, it's not just the release of energy that causes something to be spontaneous. There's got to be something else going on, at least one other thing going on. Well, in comes the concept of entropy. Entropy, we've learned about what entropy is. Entropy is known. I would say this is the poor man's definition of entropy. It's not really the definition that is a purist definition. We're going to look at entropy in a little bit different context today. Yes?
Is S like the variable piece?
Yeah, so we'll talk about delta S for a reaction. That would be the change in entropy. Yeah. And by the way, they got S. Last year I finally broke, and I thought I need to find out where that S comes from. I never knew. It turns out that when they were declaring what symbol should go with what variable, they chose S to honor somebody. It's some physicist that I never heard of before. Who knows what they did? It was a physicist, so probably nothing important.
You dropped a car, right?
Oh God.
Yeah.
Moving on. Now, in chemistry, three things that will, in general, increase the entropy of a system. When a gas is produced, gases have a lot more entropy than solids and liquids do because they're so spread apart. They're very disordered compared to solids and liquids. So producing a gas would increase entropy. Also, this last one here is dissolving a solid. Aqueous things are similar to gases. Both aqueous and gas are considered dispersed states of matter. And so dissolving a solid would also increase entropy. If you remember the one homework problem from the last chapter, we had to find the delta N of gas. There was part A, B, and C. One of them had a delta N of 0, one of them had a negative delta N, one of them had a positive. That delta N is what I'm talking about here. When we have a chance to take a certain set of reactants and produce more particles than what we started with, that increases entropy too. That makes things more scattered or disordered. You're fine. Okay. Now, our authors used this system to explain entropy. I like it really well, so I'm going to totally plagiarize the Zoom dolls on this one. We're going to look at entropy in a little bit different way in terms of the structure of matter. I want you to imagine we have this piece of glassware. This would be very expensive to actually make. It's a piece of glassware that's got two bulbs and this little channel going between the two bulbs. This is taken right out of the book. Imagine that there are 4 gas particles inside of this flask system. And now the valve is open, so a gas particle can flow from one side to another. But assume that they don't stay inside of that middle space for very long at all. So we'll be able to account for all 4 of the gas particles in one of the bulbs at any time. Now I'm going to be using terms that I don't normally use, like I'm going to use the term macro state and micro state, just to help us to conceptualize how this relates to entropy. So consider this. I'm going to be using the next slide too to kind of keep track of everything. The first macro state that we're going to observe is going to be the case where we'll have 4 gas particles on the left and none on the right. So if we have this container, this whole thing is one container, if there are 4 gas particles on the left and 0 on the right, do you think that that's possible? If we have 4 gas particles able to move around freely, would there be a moment, at least, in which all 4 particles are on one side and none on the other? Is that possible?
Equilibrium.
Now, it would not be likely, but it's possible, even for one moment, for all 4 to be on one side. I like other scenarios better, but it's possible for it. So what I would say is this. I'm going to keep track of the 4 particles with 4 different colors. Black, red, green, and blue. There they are. Now, Avani, you're saying, no, that's not possible. I would contend that it's possible for all 4 to be over here and for nothing to be over here, even for a moment. I mean, these things don't have a brain. It's not like they can determine, oh, you know, we need to spread out. So one of our arrangements would be like this. Now, so I've got all 4 particles. Each of them has a different color on the left. Is there any other possible arrangement or set of particles with these 4 colors that could be making 4 particles on the left and 0 on the right? The answer to that is no, because we only have 4 particles, and if they're all over on this side, that makes 4 and 0, and there's no other way that we can arrange the particles to be 4 and 0. So on the next slide, you don't have to write any of this down. We'll say that the macro state 1 is where we have 4 on the left and 0 on the right. And for that arrangement, there's only one possible configuration, also known as micro state. Now, if you don't understand what I'm doing here, just bear with me for a moment, because it'll become very clear in a moment. When we go to the next macro state, you'll see what I'm doing. So let's do that. Regan, not a word out of you anymore. We'll go to the next macro state, where we have 3 particles on the left and only 1 on the right. Is this possible? Well, yeah, that's possible. If we could have 4 on one side and 0 on one side, it's definitely possible that we can have 3 and 1. So how could we arrange these? I could put the black, the red,
Hey, I heard you try to throw me under the bus.
and the green. What is up, Miss Robles? I would never throw you under the
I
bus.
mean,
My steak face. Robles not
And
What's
I
this?
said-
He's griping about 1 point
And
off
I
the 50
said-
point quiz.
steak face. You
he
never
comes
taught
to me and says, "You never taught me stick fix." And I said, I don't know if you recall, I
She
didn't
goes-
get you till 2nd semester.
Mr. Moore didn't teach steak face first.
And then
That's
he
on you.
goes,
That's on you.
he
I did
goes,
the 2nd semester.
that's so funny because I did it first.
Exactly.
And I asked my kids, I said, when did you guys learn stick fix? By the time 2nd semester comes, I kind of ease up on it a little. And apparently, since he had come in late, I eased up a little.
So he-
And I go, well, who did you have first semester? And he goes, more. So,
That's why I went and took this baby.
I feel like I got narked on. Is that what just happened?
No.
no, I did. I feel like I got.
I went up to her and told her it's her fault that I got
He did. He wanted to blame me. I just gave him a quick
Oh,
stick
my
fit
gosh.
lesson.
Oh, thank you. Yeah, I've been trying all year and he won't listen. He just complains.
I gotta tell you, I'm pretty sure they were mentioned quite a few times.
I'm sure that they
Yeah,
were.
he's trying to teach it, but he just keeps complaining about him not learning it while he's teaching it.
No, I was
Yeah,
gonna
that's
like.
pretty much what happened.
I got nobody in here who had me. Nobody who can back me up.
have a
here.
class
This,
right
none of you had Miss Robles for Chem 1?
Don't you have
No.
a class right now.
You got ripped off.
Yeah.
She's great.
Only teacher who made ice cream.
I think pretty much that's true. Mr. Hevel and I have gone to the troll side on that one.
I know.
Mrs. Robles is the teacher of organic chemistry, and you'll love
There
that
is
class.
no sig figs in organic chemistry.
Nav?